Welcome to Spring LIB.
Okay. In this problem, we are asked to examine a light bulb that's emitting at a power of 120 watts, has a frequency of 5 times 10 to the 14 hertz, an efficiency of about 10%, meaning the actual power out is only 10% of the listed power of 120 watts. And we're actually given the flux of these photons, which is 1 times 10 to the 11 photons per square centimeter. So we're asked to find the energy of an individual photon, of all the photons being emitted. We're asked to look for the number of photons being emitted per second. And we're also asked for a radius such that, assuming that the photons are emitted in all directions uniformly, what radius would result in the flux that's given, number of photons per square centimeter. So we're going to start with for our equations, we'll need the equation for energy of an individual photon, which it's clear to see that the energy of a photon is proportional to its frequency by the Planck constant. The number of photons is going to simply be the total power. The number of photons per second, I should say, is going to be the total power divided by the energy per photon. In order to get flux, we can simply take the number of photons being emitted per second and divide it by the area of our sphere, assuming that they're being emitted uniformly. And we can take the area of a sphere, 4 pi r squared. For constants, the only one we'll need for this problem is the Planck constant, which I have listed in joule seconds. Okay, let's jump into it. So starting off, we can find the energy of a photon relatively straightforwardly. E equals hf. We are given the frequency of this bulb, so it's just a matter of plugging our numbers in. 6.626 e to the negative 34 joule seconds multiplied by our quoted frequency, which is 5 times 10 to the 14 hertz. And this results in a energy per photon of 3.13 times 10 to the negative 19 joules. Perhaps it would be more appropriate to use electron volts, since these are going to be extremely small energies. But since we're going to immediately use this result not in electron volts, we're not going to convert it. Now, to find the total number of photons being produced per second, we take the total power, the actual power being emitted, divided by the energy per photon. And this is important. For our power, we can't simply use the 120 watts of the bulb. We have to use the actual power output, which is, since it's 10% efficient, we need to use 0.1 times 120 watts. Because apparently 90% of the energy is being lost to things other than light, perhaps heat. Plugging in our result for the energy per photon. We can solve through. And we are left with a result of 3.622 times 10 to the 19 neutrons. So a very large number of neutrons. Not surprising. Instead of not neutrons, photons. Light. Little mistake there. So large number of photons, I should say. Now we're given a flux that's known, and we can relate that to the total number being emitted per second divided by the area of some characteristic sphere. So if we have a little point source, we have a sphere of some area, with some radius, with some resulting area, we can figure out, assuming it's emitting uniformly, what that area needs to be, and thus what that radius needs to be. So using the area of a sphere, we have 4 pi r squared, and then we can solve for r with a little bit of algebra. And as you see, we are going to be left with n over 4 pi flux. And when we put numbers in for this result, we will have 3.622 e to the negative 9 times 10 to the negative 19 to the 19, 4 pi. We can take the flux that was quoted, 1 times 10 to the 11 per square centimeter. We are going to be left with 5368.7 centimeters. This is going to be the radius of our sphere in centimeters, which is approximately 53 meters. So in order to get this flux of photons of 1 times 10 to the 11 per square centimeter, we need to be 53 meters away. So that's probably the most important result from this problem. We also, on the way, figured out total number of photons being emitted by this bulb, and we figured out the energy of each individual photon being emitted by this bulb. And I believe that is everything that was asked to be solved for. So thank you.